Welcome to Unit 2, Lesson 2. Hopefully, by the end of the lesson, I will be able, not me, you will be able to determine and interpret key features of graphs and tables in terms of the context of a problem. So that means basically we want to actually get to word problems and graphs and identifying those things. But before we get to that, I'd like to introduce some basics to you, and then tomorrow in class we'll apply all this, and we'll think about this in terms of word problems and tables and dissecting that information. Okay? So why don't you take a minute and pause the video and write this down, and we'll get busy. Okay, so we have our think about it problem. So the graph below represents the rate at which people enter a local amusement park in hundreds of people per hour after 12. The park, number one, the park has a promotional event from 6 to 9 where they offer half-price admission. Did the promotion work? Why or why not? All right, you can answer this right now. You should be able to interpret this data from the graph. And what is happening before t equals 2? That's where t equals time is 2 on the graph, and explain your answer, all right? So why don't you take a minute and pause the video and answer these questions about this particular graph. All right? So pause it and get busy. All right, now we have some things that we've already talked about before, but I just want to reintroduce these ideas to you. All right, so we have critical points. So the critical points are the max or minimum of our function, basically. That's not exactly what they are. Technically, what the critical point is anywhere where the derivative is 0 for my function. So technically, that's what a critical point is. But for the time being, for what we're doing, a critical point is strictly the max or minimum. They can be global, which means for the whole function, which means we call that an absolute maximum, all right? A global maximum is an absolute maximum because it's the absolute max that our function can be. Or we could have what we call a relative maximum, which is just the maximum on a specific interval, or minimum, right? It goes either way for a max or a min. And then we have our x-intercepts, and that's the point at which my function crosses the x-axis. The y-intercepts, that's the point at which my function crosses the y-axis. And points of inflection, that's points where my function change from concave up to concave down. We discussed this a little bit in class, but that's where my function is opening. It's opening up or opening down, and a function can have multiple concavities, which means it could be opening up in part of it and opening down in another. And we kind of see an example of that when we look at the function f of x equals x cubed. So I'd like you to be familiar with these terms because we're going to be using them. And we're going to apply it to data and graphs. All right, so we're looking at that graph from before, and what I want to do is I want to identify those points that we just talked about. All right, we have our critical points. Those are absolute maxes, mins, and whatnot. All right, so let's identify our maximums and minimums on this function, okay? And this is a function on a specific interval too, and that's kind of important, all right? So notice the top of my curve here. Let me erase that. The top of my curve here, right? Right there and right there. You see that? I hope you can see it. All right? Those are both maximums, correct? Right? But one is absolute and the other one is not. Right? This first one here is called an, sorry about the writing, guys. I'm using a different stylus today. This is called an absolute max. It's an absolute maximum or a global maximum, right? And that's because it's for the whole entire function. There is nothing that gets higher. This one here, right? It's a maximum between here and here, right? It's a maximum value, so that is called a a relative. Oh, let me write that in the right color. That's called a relative. Relative. Relative max, max, or a local max. Local because it's only right in a local neighborhood. That's that interval, that neighborhood that it is true for. Okay, and we have a minimum here, right? What is that minimum? Is that minimum a local or an absolute? Right there. Well, you have to consider your endpoints for your function. So you have these two here. These two are going to be what? They're going to be minimums, absolute minimums. So this is a local min right here. Local or relative, right? Okay. And then what else do we have? Let's look. We have our x-intercept, our y-intercept, and points of inflection, right? All right, so do I have our x-intercepts? Yes, I do. I've already circled those. Does this line cross the y-axis? No. So there's no y-intercepts. And then we have this new idea of concavity, all right? So let's look at this. So where's my function concave up and concave down? It's concave up and concave down on intervals. So from the beginning here, right, all the way to like the middle here, that part of my function here, this part here, is going to be concave up or concave down. Okay, that's like concave down, and then there's over here, it breaks up into another one, and it goes like this. And then there's in the middle, all right? So these points where it separates into different ones, so into different sections, that's this one here and this one here, right? That's called my point of inflection. It's the change in direction, okay, of concavity. All right, so hopefully you can find those critical points by looking at a graph. And we're going to talk about interval of increasing and decreasing. That's what it says, where my function is increasing and decreasing. All right, so I'm not going to go over that too much because I think you got that under control. You can figure that out on your own. All right, so let's look at some problems now. All right, so this is a nice intro into some of the stuff we're going to be doing. All right, Miguel is designing his shipping box that are... All right, I don't know where we left off. I got interrupted. Sorry about that, guys. So on this problem here, we want to maximize the volume, all right, for a box. So it helps if you, to understand where this formula comes from, if you draw a diagram. This is called a net. You should have learned about this in geometry. So I have a rectangle, all right, and my shape is going to have sides that are 8 and 10. So I have a side here, 8 and 10. So basically, because we're making a rectangle, right, we're going to cut out little corners of this rectangle. And when you fold it up, it makes our rectangular prism. Okay? And so the height of the box is h, right? And then the sides are, this is 8, and then this side is 10. Hold on. Take that back. Sorry about that, guys. I'm sick. So you want to maximize. So when you do this problem and we're maximizing, what do you think you're going to use here? What are you going to be looking for the volume? Right. This is an equation for volume, and you're looking for the max. So what you want to do is you want to take and look for the maximum. All right. and you should use your graphing calculator or Wolfram Alpha to do this. All right, so your solution to this problem will be, so you're going to get an approximate height, right? That's what the little swivels, that little thing means, is going to be approximately 2.9 with a maximum volume. So this is 2.9 feet. Right? And a volume of approximately 105.03, all right? So when you solve that, that's what you should get. So this is without a top on this problem here. And I want to find out what my formula should be for this one because it doesn't give it to me. Sorry, I was jumping ahead of myself with that last problem. So this one, I draw my sheet of paper, right, with my cutouts. All right. And I have little things, little spots I have to cut out, right? So each one of those is going to be represent the length of the side X. So each one of those is X. Now you should be able to come up with a volume, an equation for the volume. Remember, because volume equals length times width times height, okay? So you need to find the length, the width, and the height. And the whole sheet of paper is, the whole sheet of paper is 11 by 8.5, right? So this side is 11, and this whole side is 8.5, okay? So you should be able to come up with your equation from there and solve for the maximum possible volume. That's what I'd like to see, solving for the maximum possible volume. Let's look back at this other question here, all right? Really quick, the diagram for this is going to look something like this. 1, 2, we connect our corners, right? And we connect the corners. All right, and so the height is H. And then we have the width, which was H minus 10. And the length, which was H minus 8. Or it doesn't really matter which one you call which. And that was for our volume, all right? And then there's our volume for this one. What is the answer to this? Hopefully you can figure it out. We get what did we want to find? The length of the sides of the square that you cut out. So the length of the side of the square that I cut out is going to be approximately 1.6 inches. Okay? And that's a maximum volume of 66.2 inches. These are approximations, they're not exact, okay? So that's what we get. Hopefully you can figure that out. You just have to write the formula. I gave you everything you need to write the formula, and you can use your graphing calculator or Wolfram Alpha to come up with a solution. All right, this next set, you're going to have to plot the data and see what it looks like. All right, you can plot the data using a graphing calculator or an online graphing calculator. So take a minute, read the question, write it down. and plot it. Oh, but wait, I did it here for you too. Think to yourself, what does this function kind of look like it might be related to? All right, and you know, what is it doing? What shape is it? And what direction is my graph going in? All right, these are all important things to think about when you're looking at the data in the table, because we want to take and analyze that data. All right, I want you to write down this question and answer it and tell me what you can conclude, all right? So just pause the video and write this down, and I'll see you guys when you come back. I hope you have a good night.